Myself, Dr. BJD Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss about binary addition and subtraction algorithm. At the end of this video, the student will gain knowledge regarding what is binary addition, what is the process of binary addition and binary subtraction, what is the digital circuitry behind to perform binary addition and subtraction, what algorithms are available for binary addition and subtraction. The agenda of this video is introduction and examples, how to perform the binary addition and subtraction, what is the hardware requirement for binary addition and subtraction, and what is the flowchart for the binary addition and subtraction. So when an integer number, how it has to be represented in the binary positive number can be represented and the negative number can be differentiated with a sign bit. The sign bit can be the MSB bit of the number. The MSB bit, if it all 0 means the number that is the positive number. If the sign bit is 1 means the number that is represented is a negative number. So when an integer binary number is positive, the sign is represented by 0 and the magnitude by the positive binary number. When the number is negative, the sign is represented by 1. The sign bit can be represented by 1 in case of negative numbers. But the magnitude, the rest of the number can be represented by any one of the 3 possible ways. There are 3 possible ways to represent the magnitude of the negative number. One is signed magnitude representation, signed ones complement representation, signed twos complement representation. So in case of positive number, the sign bit can be the 0 and the magnitude has to be representing the positive binary number. In case of negative number, the sign bit can be 1 and there is 3 possible ways to represent this negative integer value. One is signed magnitude representation, second one is signed ones complement representation, third one is signed twos complement representation. How these 3 representations can be used, we'll discuss by taking an example. So if you want to represent plus 14, then in signed magnitude representation, the 14 binary value can be represented in the 8-bit like this, and this is the MSB bit. The MSB bit can be used to represent the sign of the number. If it contains the 0, then the number can be the positive number. So we have to represent plus 40. The plus has to be represented by putting a 0 in the MSB bit. So here it is representing the sign of the number and the magnitude can be equivalent binary number of the 14 can be represented like this. So this is the way to represent the positive integer value. The negative integer value can be represented in any one of the 3 possible ways. The first possible way is the signed magnitude representation. So minus 14, how we have to represent means the MSB can be 1 in case of to represent the negative number, and this is the magnitude of the 14 value. So this is the signed magnitude representation of minus 14. And in signed ones complement representation, the sign bit can be the 1 in order to represent the negative value, and the ones complement of 14 can be taken here as the magnitude. How the ones complement can be identified means by interchanging 0 as 1, 1 as 0. then we can get the ones complement of the number. So here we have to interchange 0 value as 1 and 1 value as 0 in order to get the ones complement representation. In the previous case, directly the binary equivalent of decimal number can be used to represent the magnitude. In the second case, the ones complement of the binary number can be represented in the magnitude. Next, in the third form is signed twos complement representation. In the signed twos complement representation, in order to represent the sign negative, the sign bit can be the 1. And here twos complement of 14 binary equivalent can be represented as the magnitude in signed twos complement representation. This is the 14 value. So here the 14 equivalent binary value in the second form we represented in the ones complement form by interchanging 0 as 1, 1 as 0. But in order to get the twos complement, we have to perform ones complement plus 1 operation to get the twos complement. So this is the twos complement equivalent of the 14 magnitude. So here the minus 40 has to be represented in twos complement representation. So integers, positive integers can be represented by putting 0 in the sign bit and the magnitude of the number can be represented. And in the negative number representation, we have three methods. One method is by indicating the sign value as 1 and the magnitude of the number can be represented. That is referred as signed magnitude representation. And in the second case, signed ones complement representation, sign can be designated with 1 and ones complement of 14 has to be represented here. And the third method is signed twos complement representation. In this, the sign bit can be represented by 1 and the twos complement value of the 14 can be represented in the magnitude value. In this way, the integers has to be represented. So, how the arithmetic addition can be performed? The addition of two numbers in the signed magnitude system has to be follows the ordinary arithmetic in the decimal arithmetic. How you are following those rules has to be followed in the signed magnitude integer addition also. If the signs are the same, we have to add the two magnitudes and give the sum as the common sign. If the signs are different, we subtract the smaller magnitude from the larger and give the result sign of the larger magnitude. How we are following in the decimal number system. So, for example, consider plus 25 plus minus 37, which has to be represented as 37 minus 25 whole minus. So, the result can have the minus sign by comparing the values of the two numbers. 37 is greater. So, the sign of the larger number has to be given to the result. And the subtracted value has to be the result. So, similar way how we are following in the decimal number system, those rules can be implemented in the signed magnitude addition of binary arithmetic. And the general rules that can be followed in case of binary addition are 0 plus 0, the sum can be 0 and carry can be 0. In case of 0 plus 1, the sum can be 1 and the carry can be 0. In case of 1 plus 0, the sum can be 1 and the carry is 0. In case of 1 plus 1, sum is 0 and the carry can be 1. For example, consider two numbers. The A value is 1011 and the B value is 0101. Now, if you want to perform the addition operation, so while performing the binary addition operation, here 1 plus 1, so here 1 plus 1, the sum can be 0 and the carry can be 1. So here the sum value can be 0 and there is a carry that can be forwarded to the next higher weight value. So here again 1 plus 0 is 1, 1 plus 1 is 0 plus 1. And here if it all 1, 0 plus 1, 1, 1 plus 1, 0 and a carry 1. So here 1 plus 0, 1, 1 plus 1, 0 with a carry 1. So this is the binary sum value after performing the arithmetic addition. So an extra bit has to be generated. So this is called the overflow. So here n number of bits, 4 bits we are taking as input, but the result can be produced as 5 bits. This extra bit we can call it as overflow bit. So these rules can be used, these binary addition rules can be used to evaluate, to perform the binary addition. Now in the signed 2's complement addition, add two numbers including their sign bits and discard any carry out of the sign bit position. So if it all extra carry is produced, that can be discarded. So addition has to be performed in the signed 2's complement addition form along with the sign bit and discard any carry bit. So here for example if you want to perform plus 6 and plus 13. So here 6 value is plus 6 and plus 13. So here and we have to perform the binary addition here. So here 0 plus 1 1 1 1 1 0 1 0 1 1 0 0 0. So this is the sum of plus 6 and plus 13 and the result both are positive numbers. The sign bit of this result can also be the positive one. Next we have to consider one more example, minus 6 plus 13. So here whenever we are representing the minus or negative number, signed 2's complement representation can be considered. So this is the 6th value. So here the 6th value 2's complement can be identified. So first we have to identify the 1's complement by interchanging 0 as 1, 1 as 0. And after that 1's complement plus 1 we have to derive the 2's complement. So here a 1 can be added here. So 0 1 1 1 5 zeros. So this is the 2's complement of the 6. So this value can be added with the 13 value. So here the minus 6 can be the negative number. 3 possible ways are there to represent the negative number. The 2's complement representation can be used to represent the negative number here. And this is the 2's complement of the 6. Plus we have to add the 13 here. So 13 value can be added here. So after addition, applying the binary addition rules, 0 plus 1 1 1 0 1 and here again 0 1 and 3 zeros. Okay, so here this is the result. So this result has to be represented in the 2's complement magnitude value in order to get the actual decimal position. So in this way the negative number can be represented in 3 forms. Generally in the calculation 2's complement form can be considered. If you want to perform the plus 6 and minus 13 operation. So here this is the plus 6. So the number can be taken as it is and the negative number 2's complement form must be used in the calculation. So here this is the number. The 1's complement of this number is this, and we have to calculate the 2's complement by adding a 1 to it, and this value can be used in the in finding the addition. And we have to apply the binary addition rules in order to identify the sum. So this is the result. Next we have to two numbers with the negative sign. So we have to calculate the 2's complement of 6 as well as 2's complement of 13, and can be added in order to get the sum value. So here this is the -6 representation. So here we have to find the 1's complement of this number, and 1's complement plus 1 is the 2's complement value. So this is the 2's complement representation of the -6. Similar way, for the -13 also we have to represent in the 2's complement form. And these two values can be added in order to find the sum value. Okay, so in this way the addition can be performed by using the binary addition rules. The positive number can be represented directly with the binary equivalent magnitude. Negative number can be represented with any one of the three means. Generally, the 2's complement magnitude form can be considered for the calculations. What is the electronic circuit that can be used to perform the binary addition? So the binary addition can be generally implemented with the full adders and the resistors. The full adder can receive 3 inputs and produces the 2 outputs. So here, if at all the first number that can be performed that can be used in the addition can be stored in the A register, and the second number can be stored in the B register. So here this is a 4-bit binary adder. The first number can be stored in the A register and the second number is stored in the B register. So here, for example, consider A is having the value 1101. So this is the A0 bit, A1, A2, A3. And B register is containing some value 0110. This is the B0, B1, B2, B3. And after adding these two, whatever value that is getting, that can be represented as S0, S1, S2, S3, and this is the carry 4. Okay, so here the first full adder has to take the 0 bit of the A register and the B register. Carry can be initially 0. So this full adder can take these 3 inputs and produces the S0, the sum value, and the carry, if at all any carry is produced, that is represented in the C1 and can be given to the next full adder. These full adders can be connected in a cascade fashion. So next full adder can be taken the 1 bit of A register as well as B register respectively, and the carry from the previous stage can be given as input to the this full adder. And what is the sum that is produced? That is represented in the S1, and carry can be given as input to the next stage full adder. So in this way, this 4-bit binary adder can be used to perform the binary addition. Next is binary subtraction. So subtraction of two signed binary numbers when negative numbers are in 2's complement form is simple. So in case of subtraction, 2's complement magnitude form can be used to represent the negative numbers. With these representation, the binary subtraction can be made simple. So take the 2's complement of the subtrahend, including the sign bit, and add it to the minute. The minute can be represented as it usually. The subtrahend has to be represented in the 2's complement form. A carry out of the sign bit is discarded. So after the addition, if extra carry is produced, that can be discarded. Whenever addition or subtraction operations is performed on two numbers which are represented using 2's complement form, if result is negative number, then the MSB is 1. Then that indicates the result is also in the signed 2's complement form. So if it all the MSB bit is 1, then that indicates that result can also be a negative and can be represented in the signed 2's complement form. And what are the general binary subtraction rules are? 0 minus 0, 0 with a borrow 0, and 1 minus 0 is 1 with a borrow 0, 1 minus 1 is 0 with a borrow 0, 0 minus 1 is 0 with a borrow 1. These are the rules that can be used in the general binary subtraction. And how the 2's complement representation can be used to find the subtraction. So here the first number, the minute has to be represented as it easily. So the first number, the minute has to be represented as it easily. And the subtrahend can be represented in the 2's complement form. So here the 1's complement form can be identified 0, 1, 0, 0, 1, 1, 1, 1. And with this the 1 has to be added in order to find the 2's complement value. So this value can be added here. The 2's complement value can be added here. And in the result, if the MSB bit is 1, it is representing the negative value. So the result can be the negative. So the result has to be represented in the 2's complement form. So the 1's complement of this sum and a 1 can be added. So this is the result of the binary subtraction. The first number can be represented as it is. Second number 2's complement can be identified and can be added. If the result contains the MSB bit 1, which indicates a negative, and 2's complement of the sum has to be taken as the subtraction result. And here for the minus 13 and minus 6 can also perform the binary subtraction. So here and the minute 2's complement has to be, and by adding a 1, And here we have to represent this 2's complement form. And we have to perform the addition of it. And here also the 1 has to be represented negative, and the 2's complement of this form, this result has to be taken into consideration. So this is the result of the binary subtraction. In this way, the addition and subtraction can be performed. So in the previous circuit that we have to discuss is used to perform the binary addition. But this circuit can be used for both the purpose for addition as well as the subtraction operation. This single circuit can be solved for the two purposes, for binary addition as well as subtraction. This has to be possible by introduction of a control line M. If M is equal to 0, this circuit can perform the addition. And when M is equal to 1, this circuit can perform the subtraction. And here this is the exclusive OR gate, and this with this gate the two numbers that has to be performed either in addition or in subtraction operation, those can be stored in the A register and B register. The corresponding bits, the 0 bits from the A register and the B register, can be given as input to the first full adder along with the carry bit. And the result that is produced from the full adder are the sum bit and the carry that can be feed forwarded to the next phase full adder. So here also the full adders has to be connected in the cascade chain. So here this exclusive OR gate can be used to represent the 2's complement of this number, along with the 1 has to be supplied with the M control line. So here in the direct, this circuit can be solved for two purposes. When M is equal to 0, A0, B0 value can be given as input to the full adder along with C0. Some S0 and carry C1 can be produced. In case of M is equal to 1, A0 and B0 2's complement can be given as input to the full adder and along with the carry C0, and it can produce the sum bit as S0 and carry bit as C1. So in this way, a single circuit can be used for two purposes, the adder as well as the subtractor. What is overflow? So in case of addition, if n number of bits can be added and the result can be produced more than this, that bit can be treated as overflow bit. So here a result that combines n plus 1 bits cannot be accommodated. So extra bit has to be generated when two numbers of n digits each are added. The sum occupies n plus 1 digits, referred as overflow occurred. So for example, if you consider the numbers 1, 0, 1, 0, 1. So here 4 bits are involved in the addition, but the sum can produce it as 5 bits. So n is 4 bits here, but n plus 1, 5 bits are produced in the result. So this extra bit can be treated as overflow bit. But this is all our electronic circuitry. So n plus 1 bit accommodating in a register is difficult. So for this reason, many computers detect the occurrence of the overflow, and when it occurs, a corresponding flip-flop is set, which can then be checked by the user. This extra bit can be stored generally in the flip-flop whenever an overflow occurs. The overflow occurred or not can be detected by examining the status bit register, the overflow bit. So when if it all overflow occurs, then that bit has to be stored in the flip-flop and can be checked the condition by the user. And here an algorithm can be used to perform this binary addition and subtraction. So addition subtraction algorithm designated the magnitude of two numbers A and B. Two numbers can be considered and can be stored in the registers A and B respectively. When the signs of A and B are identical, then add the two magnitudes and attach the sign of A to the result. When the signs of A and B are different, then compare the magnitudes and subtract the smaller number from the larger number. Choose the sign of the result to be the same as A if A greater than B, or complement the sign of A if A is less than B. If the two magnitudes are equal, subtract B from A and make the sign of the result as positive. So how the decimal system we consider in the binary number also, depending upon the sign, the corresponding addition or subtraction operation can be performed by comparing the magnitude of the two numbers that are involved in the addition or subtraction operation. So where the signed numbers are added and subtracted, it is found that there are 8 different conditions to be considered. So depending upon the sign, we have to consider 8 different conditions to be considered. So here we are taking the two numbers and with the two signs. So 4 possible conditions can be there. For each number, 4 into 2, 8 possible conditions to be considered for the algorithm evaluation. When both numbers can have the same sign, that is plus A plus B, minus A minus B. So if it all these cases, plus A plus B means add the magnitude of A and B and the result can have the plus sign. And in case of plus A minus B, then we have to check whether which number is greater. If A is greater than B, A minus B operation can be performed and the result can have the plus sign. And if at all A is less than B, B minus A operation is performed, result have the minus sign. And both are equal, A minus B can be performed and the result is having the plus sign. And if at all A is negative and B is positive, then compare the A greater than B, then we have to take my A minus B operation is performed, result is having the minus sign. And if at all A is less than B, B minus A is performed, result contains the positive sign. So here A minus B, when both signs are equal, both magnitude values are equal, A minus B can be performed and the result is having the plus sign. So in case both the numbers can have the minus signs, then A plus B and minus is the result. So if both the numbers can have the same sign, A plus B operation can be performed and the result can have the corresponding sign. And next is plus A, this is for the addition of the numbers. Now that second operation is the subtraction operation. So for the subtraction operation also, 4 possible sign conditions can be considered. So here first number has positive sign, second number is also positive. Then comparing the magnitudes, if A is greater than B, A minus B is performed and the result is having the plus sign. And if at all A is less than the B, B minus A is performed and the sign is of negative. And if A is equal to B, A minus B is performed and the result is having the plus sign. So next, if it all plus A minus B, then A plus B is to be performed and the result is plus. And minus A minus plus B, A plus B is performed, result is minus. In case of minus A minus B, checking the magnitudes, if it all A is greater than B, then A minus B is performed with the result is having the negative sign. If it all A is less than B, B minus A is performed and the result is plus. If both the magnitudes are equal, A minus B is performed with the result is having the plus sign. So, with the two numbers, the possible sign combinations and with the two operations, 8 different conditions are to be occurred and depending upon the magnitude comparison, the respective operations can be performed on the two numbers. Now, what is the hardware required for the addition and subtraction algorithm? In order to store the two values, two registers A and B are used. The first number is stored in the A register, second number is stored in the B register. The sign of the A register is stored in the AS flip-flop and the sign of B register is stored in the BS flip-flop. And here parallel adder is used to perform the addition operation. If at all any carry is produced, that is stored in the E flip-flop. Complementer is used to perform the 2's complement value and overflow can be stored in the AVF flip-flop. And here M is the mode of control. Same circuit can be used for two purposes. The control line M is used to recognize which operation is going to be performed. If at all M is equal to 0, addition operation can be implemented. When M is equal to 1, subtraction operation can be implemented. So this is the hardware requirement to implement the addition and subtraction algorithm. What is the algorithm process? So here is the flowchart. With the flowchart, the process has to be explained. So two operations we are considering. One is the subtract operation. Second one is addition operation. So the addition, the first number is called again and it is stored in the A. The second number is referred as added and it is stored in the B. In case of subtract operation, the first number is referred as minute and it is stored in the A. The second number is referred as subtrahend and it is stored in the B. After that, the signs of the two numbers can be checked. This can be performed with the exclusive operation. The sign bits can be stored in the corresponding flip-flops of the two registers A and B. So, these flip-flop values has to be compared with the help of exclusive OR operation. The exclusive OR operation for the two possible combinations 0, 0, 0, 1, 1, 0, 1, 1. So, whenever you are performing exclusive operation on this, when both the numbers contain the same sign, the output can be 0. If at all they contain the different sign, then the output can be the 1. So, in order to check when both the numbers can consist of same sign or a different sign, the exclusive OR operation can be applied. So, here if at all in case of subtraction operation, if both numbers consist of the same sign, which indicates after applying the exclusive operation, if the result is 0, then sign of A register is equal to sign of B register. Both the signs are equal. So, we have to perform the subtract operation. How we have to perform the subtract operation? The first number, the minute can be taken as easily and the second number can be represented in the 2's complement form. So B complement plus 1 can be added here. And if at all any overflow bit is generated, is stored in the ABF. And if extra bit is generated, if at all E contains 1, which indicates that A is greater than B. And we have to look into the sign A sign to 0 in order to avoid the negative 0 condition. So this is after this, if at all E is containing a 0, A is less than B. So we have to, the result has to be represented in the 2's complement. So A's complement plus 1 has to be calculated here to represent the result. So the result has to be represented in the 2's complement form in this operation. So this is the subtraction operation. So if both signs are different, then addition has to be performed. So this line has to be moved to here. So depending upon the sign checking, whether to perform the addition operation or subtraction operation can be decided. This can be decided with the exclusive OR operation, and if it all result is 0 means both the resistors, both flip-flops can consist of the same sign. So here also in the addition process also, if both are consist of the same sign, then the addition of A and B can be carried out, and if it all extra E bit is generated, extra carry is generated, that can be moved to the overflow flip-flop. So this is the way the addition can be performed. And here after checking the signs, if it all addition can be performed, and overflow E extra carry has to be moved to the overflow. So the process can be, the magnitudes are added with a micro operation A plus B, where EA is a resistor that contains E and A. If E is transferred into add overflow flip-flop ABF, if E is 1. So the magnitudes are subtracted by adding to a 2's complement of B. So here the 2's complement A plus B's complement plus 1 can be added here. And after checking the E bit, we have to decide whether A is greater than B or A is less than B. If A is greater than B, A value can be checked in order to avoid the negative 0 condition. If at all it is 0, the result can be represented in 2's complement magnitude form. So here the 2's complement of A can be calculated. In this way, the addition and subtraction algorithm can be represented the process of both binary addition and subtraction. And another variant of this is addition and subtraction with signed 2's complement data. So here the two numbers in signed 2's complement form consists of adding numbers with sign bits treated as same as the other bits of the number. A carry out of the sign bit position is discarded. The subtraction consists of first taking the 2's complement of the subtrahend and then adding it to the minuend. Here directly the 2's complement magnitude representation of number can be considered. If extra carry is produced, that can be discarded. And the hardware implementation of this 2's complement form is the BR resistor and the AC resistor can be involved in the addition and subtraction operation. Complementer and parallel adder can be used in order to perform the 2's complement magnitude representation, parallelly the addition. If at all any overflow is generated, that can be stored in the V flip-flop. So this is the simplified flowchart of the 2's complement magnitude numbers. So here in the addition, the addend is stored in the AC, addend is stored in the BR. The two numbers can be stored in the AC accumulator resistor as well as the BR resistor. Directly we have to perform the AC plus BR, and if it all overflow generated, that can be sent to the V bit and end the operation. This is for addition operation. In the subtraction operation, The minuend is stored in the accumulator and the subtrahend is stored in the BR register. So here the first minuend can be represented as easily. The subtrahend has to be represented in the 2's complement form. So BR complement plus 1 can be done in order to perform the subtraction. If at all any overflow bit is generated, that can be stored in the B. So in this way, the subtraction operation can be performed. So this is the simplified version. Why? Because the numbers has to be represented in the 2's complement magnitude form here. So in this video, we discussed about what is binary addition, what is subtraction, what are the rules that can be used in the binary addition and subtraction, what are the electronic circuitry behind to perform the addition and subtraction, and the flowcharts that are available for the process of binary addition and subtraction, how it can be reduced the complexity with the help of 2's complement magnitude representation of the numbers. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.